Welcome in, everyone. How is everyone doing today? Hi, Suo. How's it going? You've been first to stream 2 times. Congrats. And thank you for Daily Cast. You got a legendary Ruby. Yay. 406 anchors. 407 total. Nice. Right. Today, we're just going to be working on the programming language. Also, that's a little loud in my ear. Hi, Notorian. Almost at 12 points. Hmm? Uh, Thank you for the lurk, though. I appreciate it. So we'll back working on more world building. Torian went 12k. So, nice, nice. I hope that goes well. And Torian Brain's been tired today. Yeah, I feel that. Well, actually, I was gonna talk about that. I did one stream yesterday, Saturday, like I normally do. Also because, okay, well, I wanted to stream on Friday because that would have been Valentine's Day for most people. If I streamed on my normal time, I definitely couldn't do it on Friday, and also not on Saturday. Just, I swear the teachers are conspiring to give me as much homework around, uh, the around these times. Uh, Sucks, but I'm here now. I should have put an announcement about that in the Discord, but I forgot about it, and now it's today, so I don't really see a point. By the way, speaking of the Discord, you can join the Discord for announcements, schedule updates, stuff, and then the YouTube's there too. That's where VODs go. Yeah, like I was saying, we're working on the language again. Last time we ended off by kind of starting the expression parsing. I'll explain a little bit of how I want to do it, and then I'll see if I can actually do that. There's a couple of different designs I want to think about a little bit, but we'll see. This is what we had last time. We have the expression tree. This is where we're actually going to store the data. Everything around it is just kind of to make managing the expression tree and all of the different like branches easier. So this might change, but also the internal structure might change, because let's see what's the best way to explain this. Okay, so trees are a very specific data structure. Okay, so a tree, you have A. Now, above A, you have A leads to, actually this is how you normally do it. This, oh my god. Like this, that. And then you'll have B, and underneath it, you'll have like C. Right? This is how a tree works. Each parent has some number of children. Each child has some number of children. So that's what a tree is. And you can do this using an array or a list like we did here, by doing some special math, which basically is like, okay, so we have a list, a parent A. Now I want to add a child. Okay, so this is called a binary tree because each parent has 2 children. binary. So, there's a left child and a right child. That's usually how they're referred to. I think I've seen it different ways, but that's the most common. That's how you'll usually hear it. So I want to add a this is right and left, right. I want to add a right child, add B to right. Now, how do we do that? Basically, we say, okay, the index, how long is this? The list is 1 length. The list has 1. The index is 0. We'll take through like every steps of like the internals. So length is 1. Index equals, or index is 0. Use equal signs. Right, because there's one element, but everything is 0-based indexing. And that specifically, that fact is what we're going to take advantage of to make this work, so that we don't have to store it. Because the other way you could do it is you can store it like each individual child is a separate object, and each object has 2 references to children. You could do that. That's expensive memory-wise, so usually you don't. But you can. It is by far the simplest way, because everything is separated and very simple. If you want to find the left child of a certain element, you just ask it, what is the left child? Either it's none, which means there is no left child, or it's something, and you can get that. And if you want to go all the way down the tree in that direction, you just keep asking for the left child until one of them says, yeah, there is no more. Cool. So we have length 1, we have index 0. We want to add B to the right, and the specific way that we do this is that we say, okay, we'll call this tree. We say, okay, tree of 0 times 2 plus 1 is the, right, this one's left. So 2 is the right side. What that looks like is internally, tree is, you have A, and you have nothing there, and then you have nothing there. So this is your left child, and this is your right child. And why do we do it this way? Is because now, if I want to, let's say, so this is C, and this is B. So this is the index, right? This would be index 2. Index 2 is if we traverse this tree. 0, 1, 2. And then if we add C to here, this tree, yep, and there's ads. Shit. We'll explain this after the ads. I'll wait for everyone to come back so everyone can hear. I'm going to set up some stuff for the other kind of stuff that I want to explain. We got this. B. will be right back and do something. And we're back. What did I do for the rest of this? Find closing. Lexing is fine. Lex value, and then lex variable, and then lex number, and then lex string. Parse statements, parse expression. Okay. Cool. I'm going to switch to our other playlist. There we go. Okay, so we were here. Now don't worry about this, we will get to this in just a second. The reason we do it like this way, instead of just storing it in order, let's say like A, B, C, D, E, storing the children in order like that, is that now if I want to find C's child, right, if this, E, F, G, that's the letter that comes after, if I want to find B's child, this is the right one, and then that's the left one. Wait. Shit. No, this is in order, but I'll explain why this math works. That's what it was. Because, let's say I want to add a left child for C. Right is and times 2 plus 2. It doesn't matter which one is left and right as long as it's consistent, but I believe you do it this way, if I remember correctly. That's standard procedures to do it this way. So if I want to add a left child for C, I say, okay, the index of C is 2. So tree of 2 times 2 plus 1 is D. And that looks like tree equals A, B, C. So we're at 2, none, 3, 4, 5. That's what the tree structure looks like. If I wanted to add a left child for C. And now I know where everything is in order. Because I can do this math to find if C has a child, and if so, what that child is. Basically, if I want to see if C has a child, as I say, well, is this less than the length of the list? If it is, then if this is less than the length of the list, then C does have a child, unless it's none. If it's none, then there is no child, but the element is there. Because, and that highlights one of the big issues with this, is that this only works for a structure where everything is filled out, right? That's why I made this. Nope. What? Oh, do I have? Okay, whatever. That's why I made this. So what this tree looks like is we have tree equals we have A. Then A has a child, B. Then B times 2, 1 times 2 is 2, plus 1 is D, and then plus 2 is C. No, and then there needs to be none in here. And C doesn't have any children. But D does. D... what? This is element 3. 3 times 2 is 6. And then you get F, and you get E. This is a lot of wasted space. There's 3 nuns in there, because there isn't a child, but we need something there to keep the indexing right. And that's a big issue with the... It's not like a really big issue for most trees, because most trees aren't like this. This is what we call a sparse tree. It's a tree where every child isn't filled out. For example, A has a single child, but every, these other elements, right? C doesn't have any children, but D has 2 children. All of this makes this a sparse tree. And this isn't very good for storage. Especially once these get, if these get really long, it gets really, really bad. So, another relatively common structure falls under the same, it still operates as a tree, is to use a dictionary. You start with you have root, or you could call this A, or root is R, and then, or not root is R, root is, I don't know, M, because R will be what we'll use for, if we go right of M, that is MR, is B, and then ML is C, and then right of B is MRR. You don't see this as commonly. Hi, Anatarium. How's it going? Did I miss anything? No. I don't think so. Yeah, how's it going? Cookie dog? Huh? Yeah, welcome aboard. Yeah, so this is kind of, you keep making, what? Why is that F? That's D. This is E. So no matter how sparse your tree is, trying to figure out where to find your bank identification code. Ooh. That's important. How's it going? I'm doing alright. I'm explaining a little bit about trees, because we're working on an expression parsing, and I want to use a tree structure, because it's cool. I don't think this is the standard way you do this. The standard way is this method called the shunting yard algorithm, which is a way to parse the tree, or parse the expression in a very specific way. But I don't care. I'm going to do it this way because it's fun, and also I don't know if shunting yard can store expressions without having to parse it each time. I want to parse it once and then just kind of store it. Anyways, that's why I'm not using the other method. This is a also relatively common method. I haven't seen it too much. Most times when you look for like expression parsing, it'll talk about shunting yard, because it's what's used everywhere. And I'm sure there is a way to get it to do all kinds of cool things. But we're going to do it this way, because it's cool. That's basically it. Right, the benefit of using a dictionary structure where you have, like, keys is basically just this. If I take this and I say, well, we actually don't have one of those, and we don't have one of these. But now, E has a bunch of children. No. Or let's say if we do this one. So what is this? R is C. MRL is D. LR is E. LL is F. This is a lot less wasted space, and that's the point of using a dictionary for sparse trees. Specifically, if your tree has most of its elements filled out, an array or a list is by far the best way to do it because it's simple indexing. You just multiply numbers. Here, you have to do like string processing and stuff. I guess theoretically you could also just make this like numbers like this. You could say that this is 0 and this is what? 2, and this is 2, 4. 4 plus 2 is 6. This is 5. You can do this too. I think that might actually be better than string processing because, again, numbers. This is still less efficient because lists and arrays are optimized for fast access and stuff. And even though dictionaries are cool, they have to store 2 bits of data. You have to store the index and your piece of information. And then an index and then a piece of information. So, while it's not always the best, this is also one way you can do it. The reason I was thinking of using this is because expressions are usually relatively sparse. They usually don't have all of the branches filled out, so this might be better. Lastly, the other option, right, I talked about this before, is to just use nodes. This is just main, this is main and then right, this is main, then right, main, right, then left, main, right, left, then right. Just, you could do it all kinds of different ways. You could do it with integer keys. That, I assume, is probably much more efficient, actually. But this makes it easy to kind of trace back where everything is. Because this belongs to that, this belongs to this one, and then this belongs to that one. Nested lists are not that inefficient. Well, how would you do that? Give me a sec. Okay, let's copy this tree. This is the tree we're going to use. How would you do this using nested lists? Oh, I see what you mean. So like A, and then inside of A there's a parent list and two child lists. You have B, and then for example this one would be C, D. This would still be empty. C doesn't have any children, so it would just be a list C. This would be list D, E, F. Um, yeah, I could see how that works. I would have to look it up, but I would assume it has something to do with lists just being computationally, not computationally, but like memory-wise, they aren't like nested lists because you're creating so many different structures. I assume there's a lot of things to keep track of, but I actually don't know. So let's look it up. Memory tree as I have not seen this before, but could be interesting. Stored as nested list. Manage what those problems like to known categories of problems. Oh, interesting. Level order traversal of binary tree with nested lists. Oh, okay. Yeah, so this. Exactly the structure. Oh, because this is... No, okay, so this wouldn't... I don't think this is what you were talking about. But this is interesting. It's not quite the same. This is traversing a tree by... traversing the tree by level. Actually... Because I assume this is just all the same, like, linked list. Yeah, this is that. Actually, I don't know. What does AI have to say about this? Oh, let me check something. Okay. What would the... Because I know there's overhead. Is the overhead enough to make it worth it? Maybe. Maybe, actually. Yeah. Well, there's only one way you can find out. You test it. What do we got? Extras. Test up high. It's right here. Def tree parse dictionary. Tree. Is it import time it? Import time it. What do we want to generate? No, because this would be the algorithm. I actually don't know how to test memory size. Logotism? Yeah. Okay. Let's see. Python module tests memory footprint of data structure. what does that return? I don't know. Okay, for a list. Random dot rand. Yeah, random dot random find range. I don't know, 1,000. Import sys. We wouldn't be using time it. Object equals this dot get size of object. Print this. What we got? Bytes, I assume. So for example, if I had, that's 8856. And then if this is a rand int, is that 0, 1,000? Okay, so because it's just 1,000 items, I guess. Interesting. Let's say this is 100 for in range 100. What we got here? Oh, interesting. So 100 times 100 is still 10,000. Oh, wait, no, because it's only looking at the memory size, because these are all references. Okay, what else we got? We got handler. What we got? What interpreter do we have on currently? Okay, it's 312. Should work. Pip install Pimpler. This terminal. And it is our test. Test is once you've installed it. Okay. What? Oh, you need to go into the directory. Yeah, okay, I don't care. Import. Dot add. What did the library say? We got. Okay, now but how do I use it? Okay. It is. It is, yeah. What would that even be? I have no idea. As size of object. Okay. Versus just object message equals 10,000 or wait 2 1 1 and then we just do the same for 2. Okay, so relatively similar memory footprints. Interesting. Yeah. One, a nested list is not that much more expensive. I mean, it's 10,000. I assume that's in bytes. Come on. 32-bit. Okay, so that's in bits. So, and nested lists are 10,000 bits more for the same number of elements. That sounds about right. Real test is tree base equals random dot rand int -1. Well, that's what we're gonna do now. I just wanted to see if, or see how the library worked. So now we're gonna do that. HashMap is good for speed. Maybe memory efficiency? I have no idea. I don't know. Let's put 1,000. 1,000. For range 1,000 elements. Tree base equals L for L in tree base if L equals to -1, else none. Else none. Okay, so 1 tree base. Okay, let's just see how often do we get? Oh, we aren't gonna get that very often. Okay, maybe like 10. As it doesn't need to be a multiple of 2. I don't know, 1,024, I think. 1,025, I think, because it's 2 plus, right? It's 1 plus 2 plus 4, I think. Yeah, and then we'll just print the, so that's a 1 in 11 then. And 1, 0, 9, 0 through 9, no, 0 through 8. There, that's a 1 in 10. There's none of these. So base size, okay. And then we'll just make a simple parser for def parse tree to reject tree. It's IL, enumerate tree. If it's divisible by I remember this. I remember learning this. What is it? It's tree of 0. And plus, and then 2, because we can't have the first element being none. It is... Nope, not this. Oh, wait, nope. We'll do numbers here. 0. If L is not none, I guess essentially, d dot update IL. Right, is there anything else? Oh, that's simple. Def tree to nested nested tree. And then we just return that at the end. Return ret. Which equals tree of 0. If L is not none, then we need to do math. We're just gonna ignore how inefficient this is. If I is by 2, 0. Path equals path plus path plus equals wait, no, equals plus path, that's what it is. And this is index equals I. Well, x greater than 0. Minus 2 divided by 2. Else path equals minus 1 divided by 2. Yes, because we have to, because we're going backwards. And then if I is 0, and we end. And ret for path, because we have to retrace this. Parent equals parent of point. No. Wait. No. I did this wrong. This is equals 1, and this is 2. Is if parent is okay, let's trace this with something simple. If we have this tree, I swear to God, I know how this works. 2, 4, 5, 1, 7, 8. If we get this, okay, tree starts with 2, and then the element we get this, enumerate, this is shit. We need to do path like that, I think. This, and then parent is ret. And path. Parent of 0 equals L. Parent of 1 equals this. Parent of 2 equals that. I think that works, right? Return ret. Hopefully that works. I think. I'll just test it. And tree equals two-nested tree and tree two-linked tree. Nope. You watch me code and you realize how pathetic your coding skills are? And see, you always look at people who know just a little bit more than you and think that like I've experienced this, you think that you just suck. Oh, and I fucked it up. But sometimes you don't realize that they know they know more of different things more of everything. And also, you have time. You can learn. Let's see. I don't know. Fry tree. Fry tree. We'll call it that. Nope. You fucking. Nope. Fry tree. Good enough. And even if I don't like some things, especially this, I've been coding for a long time. I didn't do like language coding for a bit, but for a while, I think. Not until I got. No. Like I've been. Yeah, I've been. How do I do this? They say I've been coding for. I think a decade at this point. A little bit less than a decade at this point. You learn a lot just by doing it. Oh, fuck. Yeah, that's fine. Index minus equals 2. Index minus equals 1. Index divided by equals 2. And is that right? 0, 1, 2, 3. Yeah, no, that's why this needs to go through the entire thing. This is just starts like this. 0, 2, 1. In this one, it doesn't matter too much. The dictionary doesn't. Obviously, this one's just basically an array, but hopefully that works better if there's a bunch of like nuns in there. Maybe. Let's see, what does this do? K2 children are right, left, I think. This is 1. And then this one is 5. And 4 has... Wait, what is this? This one is 4, 4... That's not right. Because 5 doesn't have any children in this one. This is just 4 has a left and right. So why does only sees 1? Music. And I'll Oh. Because it doesn't... Because it hits 0, but it doesn't add 0 as a parent. Now we'll just do path dot path equals 0. Actually, no, greater than or equal to 0 works. And it'll have the same effect, I think. Okay, if this is greater than, same thing, and then we do path dot append 0. Wait, nope, equals 0 plus path. For still only has one child. Fuck. Okay. We have element 1. I will be right back. Be right back. I have to go do something. There is... Hopefully that's not... Alright, and we're back. Sorry about that. Someone's knocking on the door. I need to go grab something from them. 1, 0. Of 0. Oh, I know, we didn't do this. Because I would pick these ones. Wait, no, not red of 0 then. Then we have to go back to being normal red. I love debugging. Here we have 8. How the fuck did we get to -5? Or -0.5? Four divided by 2. So this is even. This gets you -2. What the hell? Oh, I'm an idiot. Index. There we go. Much better. Okay. That is... both tree structures are working. Now I don't need to print that. And then we try... we don't need system. Stop this. Dict wrapper equals nested wrapper. As size of. Let me just print this. Print. Print. Oh wait, no. S dot as size of. Oh. Oh yeah, that's not good. Huh, I didn't think about that. I guess if it's not valid, we just break. Try. And then accept, then we don't do anything. Except, not key error. Index error, I assume. Yeah, let me just pass. We do nothing. Oh, interesting. Also. For index equals I. Index is greater than 0. Same logic. If tree of index. Nope, not tree of index. It is. No. If index is divisible by 2 equals 0, let index minus equals 2. Elif index divided by 2 equals 1 minus equals 1. Index divided by equal 2. Now 2 add equals true. Because the other one, what we did is if it's not a valid, oh, sorry, what happened? So we finished this, it was a stupid error. I put I here instead of index, because we're modifying the index, not I. We actually aren't allowed to change I. Oh, and then we have head break. Well, I'm gonna finish this and I'll explain it when everyone gets back from ads. If to add if not get index is none. You don't get ads if it matters? Yeah. We'll wait for everyone else to come back from it, so just want to make sure that I explain it to everyone. I mean, I can still talk about it here. Let's explain it again. It is... Basically what happened is that what we did here is that sometimes the... Actually, this is dumb. We shouldn't do it this way. Basically, because this is a completely random list, sometimes the index, or like the parent that we're expecting, doesn't exist. And in those cases, well, a non-existent parent can have a child, so we just ignore it. So... get, I think. No. Parent of point if point when parent is greater than or equal to 0, I think. Yeah, no, if it equals 0, then to add is false, and then we break. And if to adds, then we do this. Basically, because it's random, sometimes the parent might not exist, and if it doesn't exist, then we ignore it, and I'm just doing that here too. So that's a little bit more fair. Oh, Jesus Christ, okay. That made a lot of difference. Why? Did we lose the tree structure? We're just gonna return this tree, it to tree, big wrapper, Welcome back from ads, everyone. I was just explaining that one of the things I wanted to make sure we did is this, which is basically sometimes because the list is random, it doesn't follow actual tree logic. So sometimes we see an element that does exist, but its parent doesn't exist. And in those cases, we just ignore the child. So that's what this does, and then I also implemented that here. Now we're just making something to turn everything back to a tree so that I can test if I actually, if this didn't screw up the order. For key text items. This is a list, and then we sorted. This should sort the tree by the first value. And items here. Yeah, that's how we just make sure that that works the way it does. We will need to pad the list, so we'll just add that to the top. Add to 1. Nope. Plus none. That though. Yeah. Key is not none, because key can't be none. What are we looking for? We are seeing while and this equals key. Well, and this is greater than 0. We need to essentially retrace the path. Path equals that. So it'll be this almost exactly, but in reverse. I mean, not even really in reverse. Peak song in the background? Yeah, I like it. There's a reason I have this playlist on. Next one equals 2 divided by 1. 1. If, oh wait, we actually don't need to do this. We just check if it's ret is less than or equal to key. We don't need path. Not q0, key. Then we add to len ret key +1. They are quite old. I actually don't know. When the hell did this song come out? God damn. You remember listening to them a long while ago? I didn't used to listen to a lot of electronic songs, but I don't know, it's decent background music for programming. When I'm actually doing work, I play like 1000 Foot Crutch. That's the only way to get through homework, but I find that isn't everyone's cup of tea for something that's not super like intensive. Like I know some like people would like it gaming or like while gaming, but for coding I find that people don't generally like metal in the background as much. Ret of key equals value. Never mind, that's actually the easiest. Tree from dict equals tree to dict. Def nested tree to nested to tree. Metal's a pretty well choice for focus. You would think, but it's always just worked. Also, no, that's not how we're going to do this. We're going to walk each side of the tree. No, it is a list. Ret append actually, do we even need this to be sorted? No, actually. It doesn't matter because we're not creating like nested. These are just the actual values. Parent nested and then parent equals none. Equals none. Parent is none. Okay. If ret, that's what we'll call this one. This one is ret. If ret is none, ret equals that. Parent is none. Ret dot append. or less than parent. When ret is less than parent, is it add to len ret parent plus 1. Ret of parent nested, not nested tree of 0. Ret parent equals parent times 2 or plus, what was it, plus, no, times 2 plus 1. If nested tree of 1 and nested tree of 1 is greater than 0. If when nested tree of 2 is greater than 0, so this is 1 plus 2, like that. And then this is nested tree of 2. So this logic works fine. But this one will be, so ret can't be none, ret is mandatory. Parent can be 0 though. And rename, yeah. And obviously this one. Ret equals this. Tree inner of nested tree ret 0. Nested 2 tree inner. And we return ret. Return ret. Tree from nested. What? Nested 2 tree. Oh. Picked 2 tree. Picked our nested row. Doesn't? Oh. Oops. Return ret. Assert. They should be the same. Fuck. No, less than or equal to. That's fine. Yeah, okay. So they do represent the same tree. But the nested representation is about twice the size. And Torian, you're gonna get some sleep. Cheers. Have a good sleep. I hope you get rested. You know, having to do brain stuff on not a lot of sleep hurts. The all-nighters. I haven't had to pull an all-nighter in a bit. I mean, besides for stream, but I still go to sleep after. But yeah, all-nighters sucked. It feels okay in like the moment, and then after that, Okay, I think that means what I thought it meant. Nothing broke, but we'll just take it to its limits now. Yeah, okay. That's kind of what I expected. Maybe I can tree 2 nested. Less than or equal to points. Then our parent dot extend extend times int minus 1 parent plus 1. Then we need to add one more list. Yeah, if point while that append that. Maybe that helps. Well, maybe that breaks everything also. And it broke everything. Lovely. Yes. If then nested tree is less than 1, greater than 1, and actually we don't even need that. Greater than 2. There we go. Yep, fuck. That's not right. The first element should not be. If parent Okay, let me look at this. I think I screwed something up, but I that is in this. Okay, so with open message view dot JSON x f. Yes, import JSON. I forgot. Okay, let's write indent equals 4. But oh, lovely. Okay, so do we have any? We do. We have one. Okay, so we still do need the other call. And then if 1 is greater than 0. And we don't need it for the second one though. Never mind. 2 is greater than 0. Okay, so I think that's probably as fair of a shot I can give it. Basically what's happening before is that any it would append a bunch of extra lists that weren't really necessary, because that was the easiest way to make it work. So we just clipped all of them. It still performs a little bit worse than the dictionary. It's not as bad. It used to be like twice as bad as the dictionary, but it's only, I don't know, maybe like 50% worse, I want to say. Right, that divided by, yeah, so about like 50-ish% worse, somewhere around that. Now if we take this to the absolute limits, okay, maybe we start with 1. Okay, there we go. Wait. Nope. Oh, times 100. Times 100. There we go. There we go. That is why. So, it is... Okay, that's not that bad. That says it's what? 3% worse memory-wise? I think. If I did the math right. Okay. Maybe. Okay. If we go down 1 so that it can do it more or less instantly. Okay, so 2% worse. It's not that bad, actually. If we keep going down in size. Oh, and that's 50% worse, and then it's 30% worse. Huh. But it is consistently worse. And that's what we want to find out. with some testing, it is worse. It might be better. At least it's better. It's worse for memory. The nested structure. Nested is slightly worse. It gets less worse as you get bigger and bigger, or with more data. It's like this one. I think it. Oh, never mind. That's like 30. I guess because it's just completely random. So it's some amount worse than the dictionary. Well, that was a fun side tangent. Was a good idea, though. I can see why it would definitely... Because it gives you clear ideas of which one are, like, the relationships. Because this one goes straight up to... or, like, this is the first element. This is the second element. This is the third element. So this is your root. This is your, left side or right side, I guess, depends. This is your left side or right side. Yeah, interesting. With that being said, though, I think we will probably do a dictionary structure. Just because we can. And I don't... like we said, that the array structure is probably not as good, actually. Test up high. I'm curious, what does... tree from... Huh, interesting. So even though we have a sparse... I don't know, what if we make this like 3? Okay, and now it's bad. So the array structure kind of hovers around. But as the tree gets more sparse, it just gets significantly worse. So for example, if 1 and 3 is just non-existent... Oh, interesting. Oh, and now it's significantly worse. Huh. Numbers are weird. I think probably going to use the tree structure, though. Or a dictionary. With probably elements like this. With probably like numeric elements. We don't need that. Index is 0. We don't need to pad because there's no... It's not an array. Self.struct. If in this... self.struct. dot update and val optype. Yes, like this. And we self.balance from the index that we arrived at. And it's just the same thing, but backwards. Or not backwards. It's times 2 plus 1. We don't even need the else. What do we do? Parent. If start self dot struct nope, not of start. It is parent equals dot struct of start minus 2 divided by 2. Parent of 1. Parent rec equals self dot of parent of self dot equals self dot self dot precedence of what is this? Okay. Node equals self dot struct of start. Precedence node of 1. If parent precedence is less than self dot precedence. How's this work? Then we swap places. Okay, No, so this is the right branch, which means our left branch needs to move up with us. The parent's left branch needs to move down with them. What does that look like? No. Anyways. If the parents... Yeah, so if we want to swap... How do we swap? Okay, so if we have okay. Okay, we're gonna get rid of this. Okay, we're gonna think this extra equals times 4 plus 1. Power of 5. Let's say. Okay, so we read this first. Okay, we add that node. Then we add this one to the right, and then we balance. This is index. Are we doing right is 1? I feel like that should be reversed. Yeah. This is 1. Yeah. Okay, so we add right. Our node is 2. Higher precedence, so it grabs the parent, moves it down into the left branch. Okay, so first tree equals we are going to represent it as an array though, just for ease of use. So first, the second tree equals 2. So first is before balance, and 1.5. then 2. We get this because we add the asterisk, the times, to the right side, which means that it gets added at index 2. And then we balance from here. 2 val. Index. So it grabs the 2 and then puts it in the left. This should be 2, and then and 3. You get times 2, and then you add something to the right, you get a 4. And then currently, both of these have a lower precedence. Numbers have the lowest precedence, because we're doing precedence in reverse. So numbers are the most important numbers, and other expressions are the most important. Then, you know, you have your normal operator precedence. I have this defined at the top somewhere. There. Value is 0. A modifier, so something like this, that, or that, which we'll have to figure out from context clues whether, especially like minus and plus, if that is a negative, as in like number minus another, or a negative as in a negative modifier. We'll worry about that later though. If it's a modifier symbol, it has a precedence of 1. Modifiers go first. Then after modifiers, then we have exponents. Then after that we have multiplication, addition. After that we have comparison, and then then finally we have Boolean operators. So 0 goes at the bottom. And so both of these are numbers. They have a lower precedence than their parent, and everybody's fine. So 3. Now we have 4. 4, we added this. Nope, stop. And we added a plus. And this is a 4. This plus, this belongs to the, oh wait, no, we added a this and then a plus. Plus has a higher precedence than 2. So 4 val will look like times, this will be a plus, this will be a 4, this will be a 2, and then this will be an empty. And 5 will be a times plus 4, 2, and then now on the right we have a 1. And everybody is still happy, because 1 and 2 are both less than plus. Plus and 4 are both less than times. So 5 val, and then we get the same thing. Yes, now 6, and then 0, 1, 2, 3, 4, 5, and then a 6 is this. And now everybody is unhappy. So 6 val. So that will stay the same for the first step. 4, 2. 1, so we'll do this, and then what happens, so this goes up 1, and then the 1 comes down. 1, and then empty backspace. And we have 6 val again, because now these aren't happy with or this isn't happy with plus, because plus is a lower precedence than, or plus is a shit, I did this in reverse. Plus should be at the top. Whatever. We're still gonna run through this logic just to see how we want to handle this, because lowest operator should be at the bottom. Okay, actually, we'll go back to here. Okay, we'll do it like this then. So we have 2 times, and then the 4. 4's fine. We'll go back up to here, because I fucked it up. And 4. What does 4 look like? We have the times, we have the 2, we have the 4, we have this, and then we have that symbol. This is not happy because 4 is a lower precedence than it. So 4 val look like times 2 this 4 empty. 5 will look like and this gets filled with a 5. Everyone is still happy. And then we see a plus. Now the plus is unhappy because 5 is a lower precedence. So 6 val will look like this. But now this will be plus 5 empty. And that plus is still unhappy because its parent is the, right? This is 1, 2, 3, 4. Parent is the, no, this is left, so this is -1. 0, 1, 2, 3, 4, 5. Oh, we forgot to include 2 technically has some over here. That is and the second we included this, we had this. That's why the math stopped working. And then that is fine, because now we'll just get, it's not that though, it is four. 0, 1, 2, 3, 4, 5, 5 minus 1 divided by 2 is the 2. There we go. And everyone's still happy. So this stays. Now the array is long. It's okay. Now these two elements that there's 1, 2, 3. Fine. 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then there. That is where that should be. Because the 5 is 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 6, 3, 8, 9, 10. It's minus 2. Yeah, okay. 7, 8, 9, 10, 11, 12, yes, 13, 14. So that's where that should be. Now that's unhappy because it has a higher precedence than the 5. So the 5 goes down here. This goes up. Wait, no, it's a plus. Now this moves up, and now it is still unhappy because it has a higher precedence than that. So needs to move this and the 4 down. So this is the right. This is 1, 2, minus 2, and then here. So this one becomes the parent. Now it goes here. That. And that means that this child needs to also move down to the corresponding spot. Now this is 6, 8. Plus, so 5. That's 6, 7, 8, 9, 10, 11, 12, 13. Yes. The 4 go down to here. Maybe. No, because the 4 should go here, and the 5 should go here. But how does that rule work? That rule says, because now the plus owns that and an empty spot on the left. Oh, wait, no, that's 2. So you go to the left. This and this. Now this owns this and nothing. This is 0. Oh, that doesn't work. Why is the logic fucked? The 2 and the 3, 5. The 4. The 4 was before. And that's it. Now they switch places, and then we have the 5. And it's happy again. Now the 5 owns a plus and nothing. They switch places, so now the plus owns the 5 and nothing. Or the 5 and nothing, yeah. And the plus and the exponent needs to switch places so that the plus owns the exponent and nothing. So I guess the right kind of this is the left child kind of switches places. So the parent becomes the node's left child, and the node's right child goes to the parent. Yes? Yes. Because now this owns this and that, and it shouldn't. So this owns that, and nothing. Oh, okay. So yeah, so that should then free the right spot, and this should own. So this right of the plus, which is this will make it easier to see and debug what is happening if everything is all on like a nice row, which means everything needs to be the same size. There we go. So the plus then owns this. This had a right child. The right child moves down. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So then the right child goes here, not there. And the left child of the old one becomes the right child of this one. Yes, so you keep your left child, and the left child of this one becomes your right child. So this type of balancing only works if it's from the bottom of the tree. Because if you also have a right branch, then the right branch actually gets left alone. Never mind. That works fine. And then then we have to do one more balancing. Because this doesn't want, this needs to be at the top, so which means it swaps places with the times, and the times keeps its left child, which means it's what? 1 times 2 is 2, plus 1 is the 2 goes here, and takes this one's right child. Wait. Or no, the left child becomes this new right child. And then you have to move all of yours. I don't know how we do that in a efficient way, but I know how it works now. Right, you are 4. Yeah, 4, 3, 4. And then you're just going to come up here, 5. And this is just empty. And then the balancing is done, so then when we add the 1, it finds the first right spot, which, in this case, is here. And then we're done with the expression. Obviously, because we're representing it as a dictionary, we don't have to deal with all the fucking white space. But I think that works. So we can get rid of these, because there's no balancing going on. Did you need to balance there? You didn't need to balance there, so you're fine. Okay. So if the parent has a lower precedence, than the how do we handle this? This is the and it owns that one, and then this one, the left child becomes the right child of the parent, and then the left child of the parent stays with it. And yeah, it's confusing. But I think I got it. Hopefully I got it, because we're about to implement it. Sorry, sometimes when I'm like thinking, I stop talking for a bit. Let's Do we need to store all of the parents? I'm going to store everything. I don't know. I don't like that. But I think it is what it is. I think we just have to make a copy. Okay. I will be right back. I need to go to the bathroom. We're going to put this on the be right back. Then we're going to turn the music up. See you in a bit. And we're back. And I had an idea. So instead of this existing, because that was one of the things that I was thinking about, is that the modifiers don't take two arguments. It is single argument. So modifiers just get put on top of whatever else was before it is like one term. Tarium, you're gonna tap out for the night? Good night? Have a good night. I hope you get good sleep. Good sleep is important. And take care of yourselves. Dying is bad for your health. I know. Surprising. There's 1, 2, 3. Because there are 2 types of modifiers. And that will change stuff. Because the I guess maybe this one just switches the sign, so if it's negative, it makes it positive, and if it's positive, it makes it negative. This forces it to be negative, and that forces it to be positive. Do I want to do that? Because negative switches these signs. Because the negative symbol switches the signs, and that's not quite what I'm looking for. No. That's not what we're looking for. I guess maybe we just follow math rules. Math rules is okay. Modifier. Maybe there's more after that. I know there are a couple that take multiple arguments and then yeah, so we'll treat this as same with negative. No, negatives should act immediately. Yeah, but a negative will just be like an expression. So it'll be, let's see, where we got here. Do we want to do that? I guess it's just a function that is applied to the next term. And what did we do for number? I don't think we did any of the values. Wait, did we? Yeah, we did. If we see that okay, we'll think about that later. No, that's actually kind of important to how we do this. If we say that a negative symbol is a negative symbol when we're looking for a value, that means we've already seen an operator. Then we're gonna call it a function. Or like a kind of function. it doesn't quite fit here. I think then we append modifiers. It doesn't matter. Let me say modifiers dot append. Append. It is. We append this, that, token, and a none. Okay. Yeah. So we'll keep like track of all the modifiers that are currently on. And basically if the last modifier if this is token everything tell you caused by the stormy sea you meant the world to me. If modifier is none. Yes. So basically this will be like it hasn't been applied to something yet. And we don't need this. Pass, we'll make a note to do check if the modifier can along with current. Else error. To do finish. parse find end of expression plus error. So we don't need this, but what we do need is right, so if the meant the world to me. Pass, or, we aren't gonna skip this because we're just gonna do it now. But def swap self node 1, node 2. If node 1 in self.struct else else wait self dot swap node 1 times 2 plus 1 node 2 times 2 plus 1 self dot swap and yep. If node 2 times 2 plus 1 in self.struct self.struct if node 1 times 2 plus 1 in self.struct 4 plus 1 in self.struct node 2 4 Yeah, like this if parent precedence is less than node precedence. Let's swap. Oh yeah, that's why this is a problem. Because the parents, so for the node, we are the parents. We are the parents in this case. Right side. So we are the parents' right side. And so if we swap then that's a problem. If we swap this, is it actually? So we need right back down to here. We switch with the parent almost. So we swap our left with the parent. So the parent goes all the way down to our left side. Wait, what? Parent precedence? What? No, it's on this. Parent equals this. Parent int. Parent int. There we go. So our left side becomes the parent. And the parents and then we, what if we do have a left side? What happens? here, I think. Or like here or something. Yeah, where the plus is here. That moves down to our left. The 2 moves down to this left. And our right becomes or our left. Because our left becomes the parent's left, I think. Because this is 2, 1, this is 2, 3, 4, and then plus 1. So this is a left. This becomes their right. So our that's 2. So our left swaps with the parent's right. Wait. Oh, yeah. No, that's not good. Okay, so we do know the parent. We know us, like the actual value. Okay. And see if ain't. Oh, yeah. Okay. Make this like that. There. Okay. And 1. And 2. And 3. 1 has 2. That's horrible, but it'll work. Okay. So we had this. So this is, yes, our left. If we did have a right, where would it need to go? It would need to go, it would need to stay as our right. Yep, it would need to stay with us. So for example, if here, after we added this, we put this one here. We added a 1 here. And that one would need to stay with us. So right needs to stay. Actually, one last thing. If I assume this would be the most, but class tree node, nope, init self value left right, self value self left right, def methods do we need? We need this might actually be more time efficient and actually more possible. I don't know about memory efficiency though. That's kind of our only issue. It is, we need swap, no, swap, right. Self dot right, self dot right equals node return node right, def replace left, return node left. Anyways, we don't need this. I guess even if we didn't keep track of parent, that would be fine. Actually, no, that would be bad. We do want to keep track of the parent so we can start from a node and go up the tree. What's this? Tree to tree that's equals none. So I think for, is it IL in enumerate tree. Enumerate tree. Did we do it here? We did. We need to trace the path back. This is not the most efficient way to turn it into a tree, but it's fine. Path equals this while index is greater than 0. Unappend part. Okay, no path equals r plus path. Minus equals 2. Else. L. Path. When parent is not equal to 0. For point in path, if no, we need to parent. Yes, parent is ret, and then 2add is true. Equals ret, 2add is true. Okay, if parent we'll just store something. We'll do this like this. Def get item self index less than 0 or equal to, nah, it's fine. Equal to greater than if index equals 1, return self dot left. If index equals 2, return self dot right. And none. That. So now we can, this can just be 2. And this can be 1. Same as we did for everything else. This, that. Parent equals if parent of point is none. If parent of point is none. Just return the exception. It's fine. I guess no. Raising is fine. Makes that I wanna know. If parent of point is none, to add is false, break. Parent equals parent of point. Tree to nested. Wait, not, yeah, tree to nested. If to add, yes. If to add parent up at the top. If to end parent dot parent of enough time. Index is greater than 0. So if the index is 0, equals 0, right equals 0. Oh, well. Tree node of L parents. Is true for point and path. Oh, that's fine. Tree node L. And then we check if we got it right. Is object to tree. Object to tree. victory, ret. No. I assume this can't be any more efficient than the nested list, because at least the nested list isn't a full-blown object. So, I don't know. We'll see. Oh, yeah, that's not good. I mean, that's what I thought, but also, oof. Fine, then we're doing this fully. Def 2 dict self node. Same thing as the on def. 2dig self node parent equals 0. Equals this. Oh wait, no, this is actually different, because we do have to return. Let's do if node non-self.struct, return this self.struct. And times 2 dict self.toDict parent times 2 plus 1. Turn right. Self node data parent is 0. Nope, doesn't matter, because we're making it. Struct of node equals data of parent. If parent times 2 plus 1 in data one. If parent times 2 plus 2 in data, then we do the same thing. So both of these are recursive, which actually fits because we do need that kind of just reach problem solving. Yes. So we check left, and if the data has a left, then we go grab that and add that. And then if the data has a right, then we go grab that and add that, and we don't worry about over or right. So the left, so we go down one, this left. Two plus one. We swap that with the parents left. So our left's left swaps with the parents left. Okay. Shouldn't have to worry about overwrite there. What if we do have a left one though? And this is why we wanted it, because we do need to save data for this. So we make the parent our left. Delete the self-struct of node. Node left equals node left equals self dot to dict self, and then node is start and val. This is parent. And this is parent val. Node there we go. Plus one. So are the left of our node. And then we pull that, and we do have a true. Self dot swap node times 2 plus 1 parent and then axis is right. Ignore the right side. self dot from dict. Where are we putting it? Oh, wait, actually how to fight that I could show you how to defeat the night. Node left, and then this is parent times 2 plus 2. So we grab our left branch, we make it the parent right branch. We grab our left branch, we make the parent our left branch. And then we say node 1 times 2 plus 2. Node. Yeah, that's the right side. And if we tell it to ignore the right side, then it should just pull. Defeat the night. Wait, I think the better way to do it is self dot swap node times 2 plus 1. So our left branch with the parent times 2 plus 1 with the parent's left branch. Our left branch. So we move the tree. Okay, more paint. tree, 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 maybe like tree, tree, tree. So if we select this and find where we're allowed to move it, we shall turn to the creature. Because basically we want to grab this one and put it here. Yeah, good enough. So if we pull our left set off, our left branch off, we take the parent, we set that as our left branch. And then it has no right branch now. There we go, much better. And smaller than that. So we have a thing here, that's a node, and that has a left arm. This is a node that targets a left arm, and this has a left arm. Something like this. Okay. We need to find a way to, I don't know, let's say, let's use this and we'll make this small. That's this. Orange. Yellow. Green. Blue. Rainbow. So here, I will be right back, just a sec. Alright. Kind of. At the end of the day, the goal is to do this. We grab this. Yeah, and... yeah, uh-oh. That's not what I asked for. I asked for this shape-ish. Want this to be here. This can be... and we essentially want to put that here. Now, how do we do that without... can we? I don't think we can. You can replace the parents left's left. If node 1 not in self.struct and node 2 not in self.struct, return. Swap top. point. We do just need to pull it out. Now, so the parent is pulled down, so now there's an open spot there, and then we can move up. Yeah, there really isn't a way to swap. If you're swapping within the same level, it's fine. But if you're going down levels or up levels, this method doesn't prevent data from being overridden. Unless... construct else. Node 1 not in self.struct, and it is node 2 val. If node 2 val. Oh my god, this is node 2. Yes. I believe this should be safe. I think. We can check. We check now or later? I'll check now. If name equals main. Equals 1, 1. And 1. Tree dot add one, 2. Tree dot add left. Add right. Tree dot add right. Okay, wait, no, actually we should just make it. Base tree. Tree to date. This one. X tree. Equals random randint. Import this name random. Maybe like 10 elements. We'll just do it like this. I don't know. M. Like that. predict 0, assert. Okay, well, I mean, if it's equal, then okay, that's cool. And then state wrapper and next. Let's just make sure that it's like 0, 1. Okay, cool. Then we xtree, nope, xtree dot swap. Node 1 equals inputs. Node 2 equals inputs. Node 1, node 2. Node 1, node 2. -5 to 5, no, -5 to 10. N equals 0. I don't know, 3, and then 4, 3, and 4. Okay. Okay. Let's do this again. We got 4 and then 2. Did anything change? No? It's fine. I don't know. 1 and 3. What is 3's children? 1 is 7. And this is the which children? This is the left. So 0M. Nice. Seven was fine. Does 3 have other children? 3, is it 7? Does 7 have children? No. So it would be 7 and be 8. Do we have an 8 in here? No. 4 has 9, but 4 also has 10. So it's 3, would be 7, and then 8. 8 gets 10. Oh. Whoops. Yes. Self-destruct. Okay, well that looks like it works just fine. That's good. Question. What if we see, I don't know, 1 and 4. 1, 4. And everything breaks. Key error 3. And 3. So 3 moved up 1. So 4 became 8. 4. Oh, because right, 4 is right child of 1. So yeah. Okay, but what if we do like temp equals input x and then this is a left. The left side. And 3's left side stayed the same, but the right side got changed to 1's left side. Okay, yeah. No, it did exactly what we wanted it to. What happened to 9? 9 is left of 4. Left of 4? Yeah. Where did 9 go? That's 6. That... Okay, well, that works then. So what does the balance need to do? Balance, we grab our left side. No, we don't need one. We don't want it to do that. So node left. So our left branch gets replaces the parent. Yeah. And this just move fully up. Yes. And then this moves down and replaces the parent right, which currently there's nothing. No. Unless we... maybe we self dot swap node times 2 plus 1 node times 2 plus 2. Oh wait, no, no. With times 2 plus 2. So we replace, so it replaces its own right branch. And then the parent comes down without replacing, without worrying about the right side. Okay, we'll just make sure this works first. So we grab our left branch, then we put the parent down. And then we put our left branch as the parent's right. So now the parent is our left. and then alright is alright. Alright stays there, and then we just move us up. Self dot swap node with the parent node. You should just make one that's move def move self node 1 node 2 x is equal none. Well, no, we're moving node 1 to node 2, so we don't care if node 2 is non-self.struct. Return if access is none. Nodes, we just not in x's. Self dot move self.struct node 2 equals node 1 val, and then we're done. So move only moves all of the contents of node 1 to node 2, and that is move. We move node 1 to node 2, but we don't worry about copying everything back because it's all fucked up. Which is also how we would get away with this. We move ourselves onto the branch, remove the left branch onto its right branch. So we just move. And then we move the parent down. See, this should work. Hopefully. So we move node 1. Yeah, no. This one doesn't need to delete. Another season. Another season. And so this will be the exact opposite sequence if it's on the other side. Node -1. Parent val same. Our right branch moves on to its left branch, and self.move, we move, no, we move our parent onto our right branch, and then we move to the parent's position. Okay, yep, no, that hopefully works. Can we make this more close to 1? Equals nodes divided by 2. Let's try this, because there's so much overlap. I don't want to just oh, axis. Yeah, don't worry about the this is right, and this should be left. Left side equals 0, else left. That one's the only one that's going to need to change like that. This should be 0 and then 1 otherwise. Minus side. Plus side. Does this make the code more readable? No, that makes it horrible, so never mind. Ignore all of this. We're just going to leave it like this. It's good enough. Alright. I think we're going to end it here today. Next time, we're going to test this. I'm just chatting. Cool. Yeah, thank you all so much for watching. I really appreciate it. Remember to take care of yourself. Dying is bad for your health. If you want to join the Discord, there is announcements, schedule updates, stuff like that there. This VOD will be posted to YouTube, like, today, probably. Besides that, we're gonna go find someone to raid. I think I know who I'm gonna raid, though. We're gonna go check in real quick. Oop. Hello? Yeah, you're not happy. Oh, lovely. Okay. We will be raiding Ayane, if you know who she is. She's a really nice person. She plays a bunch of cozy games. So let's go say hi. So raid. This is the raid message. Top one is if you aren't subbed. Bottom one is if you are. Again, I appreciate you watching. Try not to overwork yourself. Remember, drink water. Remember, eat food. Dying is bad for your health, like I said. And I will see y'all next time. Have a great rest of your day. Bye.